Alright, in this video we're going to be talking about the concept of discontinuity of a function, and we're going to be looking at two very peculiar examples. So the first one is a simple parabola, so it's a parabolic equation. We have y equals to x squared. Now, if we look at this function from either side, so from the left or the right, we can notice two things. The first thing is that this function is very smooth, so it doesn't have any peaks or any kind of sharp edges or anything like that. And the second thing about it is that it keeps going and it's very continuous. Everything in it is connected. So if you grab a point over here, that point is connected to the next point and then the next point and so on. So you can look at it from any angle or from any point and the whole thing is connected. It's a bunch of points that are continuously connected. Now, our definition of a continuous function in the last video was that if you have the same value of the function as the for when you take the limit of the function as a value of x approaches a certain specific value, then we say it is continuous at that point. So if I were to choose an arbitrary point x here, which I'm gonna call a, then what that means is that we should see the exact same value if we approach this from either the left hand side or the right hand side, and that's gonna tell us that this is a continuous function. Now, another way in which we can say that the function is continuous is by saying that the limit as x approaches the value a of some function f of x, so I'm just going to generalize this even further, is going to be equal to just the value of x at that point. So that would be the value f of a. Okay, so that's one definition. But of course we have the other definition that if the limit as x goes to a from the positive side of f of x is equal to the limit as x goes to a from the negative side, from the left hand side of f of x, and they're both equal to the exact same value of the function f at a, then we say that the function is continuous at that point. And of course we could check this for every single point over here, so we could choose something here, for example, approach that point from both sides, then choose another point over here, approach the point from both sides, and we would essentially get the same thing. So it means that this function as a whole is continuous. So generally we would say that x or y in this case is continuous on x as part of the real numbers. Okay, so for all values of x that are real numbers, we're going to have a continuous function x squared. So that's our general definition. Now, if we look at another example, this is something that we would call a piecewise function. So, piecewise function. So, piecewise means that it is split into two sections, and it can also be split into more than two sections, and they're still considered piecewise functions. These ones occur quite a lot in fields like physics and engineering, where you have things that may not actually be continuous. And the way they work is you may have a function that is defined as a specific value or function for only specific values of x. So in this case, what we notice is that we have a function y that is constant, and it has a constant value 3 for all values of x that are less than 1. So once it gets to this value x equals 1, it is no longer defined, so it has no value there. But if you choose a value x is greater than 1, then what that means is that you're going to have a function that is going like this. And in fact, if I were to actually denote this properly, I would need to make this a hollow circle. So this little hollow circle means that it is a continuous function except for this point at which it is not defined. Same with this one, it is not defined at this point, but for any value larger than x, so it could be 1.0001, it would be defined by this value. So what do you think happens at that point, where we say that the function is undefined? And that's actually quite an important concept, because if it is undefined, then what do you think is going to happen to the limit as the function approaches that? So in this case, we can't really say anything. We can say that, okay, so let's grab limit as x approaches 1. But remember, we have two options. We can approach it from this side, which would mean we will approach it from this line, or we can approach it from the right hand side, which means that we're basically running along this line over here. So if we say limit as x is 1 from the positive side of this function y, we actually don't have anything. It is undefined. The limit does not exist. And that immediately tells you that you have a discontinuous function. If the limit does not exist, or if it is undefined, then you have a discontinuity at that point. The same thing happens if you grab the limit of x approaches 1 from the negative side of this function y. It is also undefined. Now, let's see what happens when you have something like this. So if I fill in this circle, then that means I am including the point 1 for this function, which means I would have to change this bound to just greater or equal to 1, which would still make mathematical sense because it would include this point. This one does not include 1, so we have filled out every single point along the x-axis from minus infinity to infinity. Now, what do you think is going to be the case now? Well, this is still going to be undefined because we know that the value of the function here is not going to be, essentially it's just going to be undefined. However, if we approach it from this side, then we're going to get the value 1 because now we have a definite value at this point. So if we look at it from this side, we actually have a defined value of 1. So in that situation, what do you think we can say about the function? Well, it is still discontinuous because you don't get the same value if you do it from both sides. So essentially, if you try to approach it from here, you would still be sitting at 3. If you approach the value x equals 1 from the right hand side, you're actually approaching the value 1. So the values do not match, which means that this property over here is not satisfied, and as a result, the function is discontinuous. And there are some very important applications of this because in the next video we're going to see that there are functions that can give you very wild results, and they're very smooth, but they're discontinuous at only a single point in x, and we can see how that's going to affect our results.